Hi friends, in the last lecture we defined the open ball, the open set and the metric space. Now for those of you who have missed the last lecture, I'll provide the link to it in the description down below. Now in this lesson we'll be going through a theorem concerning open sets in a metric space. So without further ado, let's jump straight into our theorem. So theorem 1. Let X be a metric space then we have the following four statements. The space X and the empty set phi are open. Second statement, the union of any family of open sets is open. Third statement, the intersection of any finite number of open sets, or you could say if any finite intersection of open sets is again open, right? It's open. In the final statement, if X and Y are any two distinct points in X, then there exists two open sets U and V such that X belongs to U, Y belongs to V, and U intersection V is empty. So let's prove the theorem. So our first statement, the empty set phi and the entire space X are open, right? That's what we're supposed to prove. So first we shall prove that the empty set phi is open. To prove that the empty set phi is open, right? Now the empty set phi is devoid of any points, right? First of all, it's empty, like. So then it doesn't have any point which does not, disobey the condition for an open set, right? It does not have any point which does not have an open ball centered at it, which is not contained in phi. Therefore, phi must be open, right? So phi is trivially open. Now, since phi is empty, it has no point in it. Which does not have an open ball which is completely contained in phi. I hope this is clear. Therefore, phi must be trivially empty. Phi is trivially empty. Phi is trivially empty. Sorry, phi is trivially open. I should be open. Next, we should prove that the entire space X is open, right? Now, the entire space X, encompasses every point in it, right? It's the entire space. So, it has no point, which does not have an open ball, which is completely contained in it, right? Every point in X must essentially contain at least one open ball, which is completely contained in X. Therefore, X must be trivially open, right? So, since X is the entire set, entire space, every point in X must essentially contain at least one open ball centered about it, which is completely contained in X, completely contained in X. Therefore, X is trivially open, right? How do you prove that a set is an open set? We prove that every point in that set has at least one open ball which is completely contained in the set, right? So then, if that is the case, then the set must be open. So that's what we did there. So next we should prove that the union of any family of open sets is open. Prove that the union of any family of open sets is open, right? How do you prove this? We take a number of open sets, right? So let A1, A2, etc., A3, etc. be any. Okay, let's we take it as a family, right? So be any family of open sets, right? Now we need to prove that A equals union I or AI is open, right? We need to prove that their union is open, right? So we take A to be their union and we need to prove that A is open. So what do we do? We take any arbitrary point X, right? Take any arbitrary X element of A equals union AI, right? So if X is an element of union AI, this implies X element of AI for some I, right? I think it's clear, right? So, but then AI is open, right? Now X element of AI and AI is open, and since AI is open, and since X element of AI, what does that mean? Then by the condition of openness, right? By the condition of an open set, there must be some open ball centered about X, which must be completely contained in AI, right? Now, which implies there exists some open ball BR of X, which is completely contained in AI for some positive r greater than 0. For positive real number r greater than 0. Right. Now what? If Br of x is contained in AI, this means that Br of x is obviously contained in union AI, right? This implies Br of x is contained in AI, which is equal to A, the union, right? This implies A equals union AI is open. Hope that's clear. Next, we should prove that any finite intersection of open sets is open, right? So third one, to prove that any finite intersection of open sets is open. So let's take two open sets, right? Let's take any two open sets. That's A1 and A2. Be any two open sets. To prove that A1 intersection A2 is open, right? That's what we're supposed to prove. So how do we do it? We take any arbitrary point x element of A1 intersection A2, right? Take any arbitrary point x element of A1 intersection A2. If x is an element of A1 intersection A2, this implies x element of A1 and x element of A2, right? Now, A1 is open, right? Now, A1 is open and x element of A1. What does this imply? This implies, since A1 is open, there must be some open ball centered about x which is completely contained in A1, right? This implies there exists some open ball BR1 of x, okay? We call it BR1 of x for some R1 greater than 0 such that BR1 of x is completely contained in A1. Now similarly, since A2 is open and x element of A2, again there exists some open ball BR2 of x for some R2 greater than 0 such that BR2 of x is contained in A2. So A2 is open and x element of A2 implies just like this. There exists some open ball B sub R2 of x for some R2 greater than 0, such that BR2 of x is contained in A2, right? Now we take the minimum value of these R1 and R2, we take the minimum value of R1 and R2 and we call it R, okay? Take R equals minimum value of R1 and R2. And what does this imply? This implies then BR of x must be contained in A1 intersection A2, right? A1 intersection A2. I think it's clear. It's pretty obvious from this because we have BR1 of x contained in A1 and BR2 of x contained in A2, and we take the minimum value of R1 and R2 and we obtain another open ball with radius r, which is the minimum value of r1 and r2. So it must be obviously contained in the intersection of a1 and a2, right? So Vr of x is contained in a1 and a2. What does this mean? So an open ball is contained in a1 intersection a2, implies that a1 intersection a2 is open. That's our proof for the third statement. So next we shall prove the fourth statement. So what was the fourth statement? Given any two distinct points x and y in the metric space X, there exists two open sets U and V, such that x element of U, y element of V, and U intersection V equals 5, right? Fourth one. We're given two distinct points x and y. Two points x and y in X. We're supposed to prove that there exist open sets, two open sets U and V, such that x element of U, y element of V, and their intersection should be empty, right? Okay, so now we're given two distinct points x and y in X, right? So we'll just draw it here and just as an abstract representation. So I'll just draw an x, the space x here, and 2 points x and y, two distinct points x and y. They're distinct. Please note that distinct points x and y. Okay. Now, so x and y are distinct points, right? X and y are distinct points implies what? Implies what? The distance, right? The distance between x and y should be non-zero, right? D of xy is greater than 0. This distance should be non-zero. Now, choose some value r. Okay, now we choose some value r, which is half of this distance. Okay, choose r equals half of d of xy. Alright, so I'm just going to draw this distance over here. I'm just going to place it over here. So, right, this is approximately half, okay, d of xy. So this is d of xy, this length d of xy. And I'm going to take half of this. Okay, take half of this. So, choose r which is less than half of this, right? Not half, equal to half. So we choose an r which is less than half of this. So we'll get to that. So here I am going to represent half of d of xy. So this is half of d of xy, right? This is half of d of xy. Again, this is also half of d of xy. Now we choose some r which is less than this length, right? Which is smaller than this length. So let me just take this small piece of this segment and call this r. So this r. I'm just going to put it over here. Okay, wait. So this small length r. This is the small length r. And using that small length r, I'm going to construct two open balls centered at x and y over here. So let's u equals br of x and v equals br of y. So I'm going to draw it here with radius r. I'm going to draw two circles over here. And this is u equals br of x, and this is v equals br of y. Okay. Now, since they are open balls, they're clearly open sets, right? So this implies So U and V are two open sets, right? Two open sets. So we proved that there exist two open sets U and V which contain X and Y, right? So it remains to prove that. U intersection V is phi. We have to prove that. So it remains for us to prove that U intersection V is empty, right? This is what we are supposed to prove finally. U intersection V is empty. So we're going to prove this by contradiction. Proof by contradiction. So how do we do this? If possible, we assume that this is non-empty. Okay? If possible, assume that U intersection V is non-empty. If U intersection V is non-empty, there must be some point Z which is a member of U intersection V, right? This implies there exists some Z element of U intersection V, right? So if Z is an element of U intersection V, this implies Z element of U and Z element of V. Okay. Z element of U and Z element of V. Now, here U is an open ball, right? BR of X. And Z is an element of that open ball. So if Z belongs to this open ball, so I'm going to draw Z over here. Just going to plot Z over here. Let me just put it over here, Z. Okay. This Z and this point at the center, that's X, right? The distance between them should be less than R, right? Because it lies within the open ball. So Z element of U implies D of X comma Z must be less than R, right? Must be less than R. Again, Z element of V implies D of, so we're going to put Z over here. D of YZ must be less than R, right? Now, we're going to add these two inequalities. So adding them up, we get D of XZ plus D of YZ less than 2R. Okay. D of XZ plus D of YZ less than 2R. Now what? Now we know that the triangle, this kind of looks like that expression from triangle inequality, right? So we'll look into our triangle inequality. Applying the triangle inequality, what do we get? We know that D of XZ plus D of YZ is greater than D of XY, right? So applying the triangle inequality, we get D of XY less than D of XZ plus D of YZ, right? Now this is less than 2R, which implies D of XY is less than 2R. Okay, we got D of XY less than 2R here. But then look at our choice of our value of R. We chose R less than half D of XY, right? What does this imply? D of XY is greater than 2R, right? But then finally we got here with this assumption that U intersection V is non-empty, we got D of XY less than 2R, which contradicts our choice of value of R, right? So our assumption that U intersection V is non-empty is false. Therefore, U intersection V, so this is a contradiction. Therefore, U intersection V must be empty. So, here's our proof. Thanks for watching.